This is Lecture 2 for Week 2 for Paper 41, Sections 2, 3, and 4. And I'm Dick Bain, the instructor for this paper. Section 2. Slide 2 illustrates how energy is distributed throughout the system of Satania. The master physical controller on Jerusalem appears to be the being who ultimately determines the distribution of energy, but it is the power center who actually does the energy distribution to the energy manipulators. The authors emphasize that it is a cooperative effort between the two entities. We are not informed about how the energy is ultimately used, but in another place we are informed that some of the energy is used to sustain stars indefinitely that would otherwise burn out. Undoubtedly, some of the energy that reaches the planets sustains the spirit beings present and also is used by them in various ways in their work on each planet. The third slide shows the analogy the authors make between the mechanism of photosynthesis and the transformations achieved by the power directors and the physical controllers. Just as photosynthesis turns sunlight into food for plants, which ultimately provide food for us and other animals, energy is transformed into other forms that can be used for various purposes within each solar system. As we look at this slide, we should pause to consider that even the lowest level controllers are actually living beings, but they are designed only to do their jobs, not to contemplate the meaning of existence as we do. The fourth slide shows that the physical controllers are not just automatons, only obeying orders. They apparently must be able to reason and make judgments. They need data from a staff of experts in order to account for and compensate for all the influences that affect the distribution of energy in their area of control. And the experts must use telescopes or other sorts of instruments to measure and calculate the influence of the items shown in the slide. The fifth slide illustrates how Urantia is shielded from the energy currents of the Satania system and the Urantia constellation levels. The authors seem to indicate that we encounter some problems because the controllers have trouble insulating Urantia against the powerful Urantia currents. They mention energy misbehavior on Urantia, but don't specify what sort of misbehavior we encounter. I have shown an energy leakage that might account for this misbehavior, whatever it may be. Note, this energy is of a higher form that our scientists have not yet discovered. The authors give lots of numbers in paper 41. Perhaps they knew that someone would eventually use them to calculate sizes and other parameters about the various sections of our superuniverse. These calculations are valuable because the results tell us whether the numbers given are reasonable. Section 2 begins with one such number. Satania has about 2,000 brilliant suns. Using this number and knowing the average density of stars in the vicinity of Urantia, one could calculate the approximate size of Satania as well as the distance to Jerusalem from the edge of the system. According to Wikipedia, there are 32 star systems within 14 light years of Urantia, but some of these are double stars and one is a triple star. Perhaps a student would care to do the calculations and let us know how large Satania is and how far we may be from Jerusalem according to the figure given by the authors. In slide 6, I have tried to use the figures given by the authors to determine how many systems have brilliant stars and how many such stars have inhabited planets. 1 in 3 seems on the high side. In paper 15, the authors say this: in your superuniverse, not one cool planet in 40 is habitable by beings of your order. This might lead us to think that the 1 in 3 number is wrong, but notice the qualifier, beings of your order. Since we don't know how narrowly the authors define of your order, it's difficult to draw any conclusions from this statement. But since Urantia is still under construction, there are likely sections that are not yet inhabited, and therefore the average density of inhabited planets in all of Urantia must be far less than that in the inhabited portions. Slide 7 combines numbers from paper 41 to show how many inhabited planets there are per astronomical system in Satania. Slide 7 also shows the numbers you calculate if you assume that most beings are of the same order as we are. Non-breathers are an obvious exception. 4 planets per astronomical system isn't totally unreasonable considering the number of exoplanets being found by our astronomers, nearly 500 by the end of 2010. The calculations in slides 6 and 7 ignore the idea that the Sun may have more than one inhabited planet, and many stars are double stars, and a few are triple star systems. However, the numbers calculated give a relative idea of the density of stars in systems, and so forth. The 8th slide shows the contrast between the size of the stars Antares, Arcturus, and our Sun. The authors state that the radius of Antares is 450 times that of our Sun. This figure is close to the figure that astronomers give for Antares. However, the volume of Antares given in the Urantia Book compared to our Sun seems to be in error. Since volume varies as the cube of the ratio of the radii, the volume of Antares should be about 91 million times that of our Sun, as shown in slide 9. It seems likely that this error was in whatever source the authors used for this section of paper 41. Slide 10 shows the expanding cloud of gas left from Tycho Brahe's nova of 1572 AD. The website ubthenews.com tells us why this reference is important, and I quote, "The Urantia Book states that the most recent of the major cosmic eruptions was the extraordinary double star explosion, the light of which reached Earth in AD 1572. This conflagration was so intense that the explosion was clearly visible in broad daylight. The explosion to which the Urantia Book refers has come to be known as Tycho Brahe's nova. It was not until several decades after the Urantia Book was published that astronomers determined that, in all likelihood, a double or binary star relationship, in which star eventually accretes a critical amount of matter from the other star, is responsible for the explosion of this supernova. In 2004, researchers announced that they believed they have discovered the remnant of the companion star that gave rise to this explosion." Unquote. One of the so-called standard candles that astronomers use to measure the distance to other galaxies is mentioned in paper 41. This standard candle is the Cepheid variable star. Because there is a constant relationship between the period of the star and its brightness, astronomers can determine the distance to a particular Cepheid variable star, and thus determine the distance to a feature in our galaxy or the distance to another galaxy that contains the star. Edwin Hubble was the first to calculate the distance to the Andromeda galaxy using Cepheid variable stars as a measuring stick. Unfortunately, he used the wrong population of variable stars and measured something less than 1 million light years to Andromeda. It wasn't until the 1950s that Walter Beatty discovered this and recalculated the distance as something less than 2 million light years, as shown in slide 12. Using Cepheid variable stars and other methods, astronomers currently put the distance at approximately 2.4 million light years. Slide 13 shows the Sun at solar minimum and solar maximum. At maximum, the Sun exhibits many sunspots, areas that are relatively cooler than the rest of the Sun. As mentioned by the authors, the interval between the maximum and minimum activity averages 11½ years. Section 4. In Section 4, the authors tell us that our estimate of the Sun's mass is low, but they don't say how much it actually is. As explained in slide 14, it appears that our astronomers' estimate of the Sun's mass has not changed since the 1930s. In Section 4, paragraph 4, the authors state, "One of your nearby suns, which started life with about the same mass as yours, has now contracted almost to the size of Urantia, having become 40,000 times as dense as your Sun. The weight of this hot, cold, gaseous solid is about 1 ton per cubic inch, and still the Sun shines with a faint reddish glow, the senile glimmer of a dying monarch of light." Unquote. But in Section 8, the authors state, "In the Sun's destined to burn out, the height of luminosity is attained at the point of hydrogen exhaustion. Subsequent to this point, brilliance is maintained by the resultant process of gravity contraction. Eventually, such a star will become a so-called white dwarf, a highly condensed sphere." Unquote. Slide 15 shows the life sequence our astronomers believe stars like the Sun pass through. This sequence ends with a white dwarf, which agrees with Section 8, but not with Section 4.4. According to our astronomers, red dwarf stars are not the end stages of star evolution, but are formed as red dwarfs. Slides 16 and 17 show a comparison between stars of various sizes. While Antares is the largest star in our part of the galaxy, the authors tell us that there are even larger stars. This concludes the lecture on paper 41, sections 2, 3, and 4.